Welcome back, everyone. We have our own Caroline Wormell from University of Sydney, who's going to talk about spectral errors in data-driven methods.
Great, thanks. Okay, so I guess what I'm going to try to talk about today is really two things. One of them was extending some work that I guess, let's say that Julia and Oscar and I have sort of had been looking at about studying extended EDMD, which is a data-driven recruitment method in a very simple setting, some of which if you're from chaotic systems, you'll be very familiar with. So understand the area of this. But when I was doing this, I sort of, was looking at these methods and I was like, actually, you can do something very general with this, the kind of ideas in this to like actually get some algorithm that can apply to any kind of, sampled operator for EDMD, but also if you have any other kinds of sort of, least squares type operator approximation problem and you want to understand what your eigenvalues and maybe even your eigenvectors are doing. So two parts to this talk. I'll talk about the theory first, the first half that I kind of abandoned, and then I'll talk about the rest. So just a kind of refresher for those who are not familiar with it. So kind of what we're trying to, the thing we're trying to look for when we're doing all the numerics I'm going to tell you about, what we call resonances of a dynamical system. So we have some F. I think of these, the kind of prototypical dynamical system as a chaotic system, maybe it's one with some hyperbolicity because that's, I guess, where I come from. And it has, let's say it has some ergodic invariant measure mu. Typically we think of this as like the physical measure. So if I randomly choose with respect to Lebesgue measure, a point in my phase space and I run my system for a long time, all my Birkhoff averages will converge to averages with respect to this measure. Typically it has some regularity. It lives in some space of measures, nice space of measures, where, let's say, its Koopman operator has some spectral some spectrum, and what we find are these, there's some mixing properties. Let's say maybe that's more important. And we find that if we study the mixing properties of this system F with respect to this measure mu, so I look at correlations, I can actually do a kind of expansion of my correlations. As my time n goes to infinity, I can actually write the kind of behavior of this as a sum of exponentially decaying functions. And so in this case, I'm just pretending that all of these functions are like, I only have like simple, anyway, I only have simple eigenvalues in this talk. Like just don't pretend everything is simple. In the same way, like with these real Polycott resonances, I'm assuming that they're simple as well. You can think of them as like really being spectral, well, yeah, eigenvalues of the Koopman operator in some kind of, idealized setting. Perhaps even in some real settings, you can find Banach spaces where this kind of spectral, where, yeah, basically this Koopman operator has like a, sorry about that. Let's turn this on so we don't lose our, good, sorry, yeah. Okay, so basically, like we kind of want to think about the Koopman operators having some spectrum. There's some canonical spectrum which lives mostly inside the unit circle, called these real Polycott resonances. You can, I guess, look at them if you're interested in the kind of, L2 picture. These are like they actually correspond to poles of spectral measures. If you analytically extend into your spectral measure density, this is what they are. The kind of semi-trivial example of what they might be is if I just look at the first order, the first eigenvalue, first resonance. The first resonance is going to be 1. And you imagine as you take n to infinity, these here, under some ergodic mixing behavior, these two should decorrelate. And my average of like kind of my sort of, I guess, expectation of like what these should be on average, the average of these two quantities should just be like what you get if you had like independence, which is basically integrating both of them separately against the measure. These are kind of, these resonances have some application utility because you can use them to sort of identify patterns in your system, maybe metastable sets, and to some extent they're what you would use to make long-range predictions. So if I had some initial state psi and I wanted to make a prediction about the future, of the future of some observable phi, then I would perhaps want to think about this expansion. All right. So that's kind of, so the kind of goal of what I'm talking about here is we really want to find these resonances. And hopefully the kind of corresponding eigenvectors. So one of these is a Koopman eigenfunction and the other is, I guess, maybe something we would call a Koopman mode, depending on how we define a Koopman mode. So how can we do this? There's, at least in certain settings, it appears that we can use extended dynamical mode decomposition to do this. So if you're unfamiliar with extended dynamical mode decomposition, you can think of it as like a generalization of something like Wormell's method. But to functions, instead of approximating your transfer operator or your Koopman operator on hat functions, you can approximate it on any kind of function. And often when you do Wormell's method, you sort of take, so I'm just, those of you who are very familiar with EDMD, I'm just, talking about a sort of more transfer operating method. You take some points, you have a bin, you take some points and you see where they go. Just you sort of try and estimate the transfer operator, or indeed the sort of future behavior of. So you imagine here I'm in this bin. I want to see what, say, the chance that I live in this bin is, or basically the expected likelihood of me living in this bin given I'm there. Yeah. Oh, cool. Yes, of course. Sorry, this was a problem in previous ones. So in some sense, we look at this is the hat of this bin. Well, okay, so this set is a bin. There are some other bins. I'm interested in a function that's 1 on this bin and 0 elsewhere. I kind of try and estimate there's 1 C of f of x for x living in here. And I use this to construct my Koopman operator, which is basically the adjoint of the transfer operator. We do a similar thing with EDMD, but I'll explain it a bit more clearly in a bit. The thing about this is that we have, okay, so to do this kind of computer approximation of this operator K, which is acting on an infinite dimensional space, we have to project down to a finite vector space because computers are finite, much as many are trying to make them basically infinite in size. So we had to project our operator onto a finite vector space, which introduces an error. So if we think about the spectrum of our Koopman operator, the spectrum of a projection of this Koopman operator onto that vector space will have a different spectrum. So we need to consider the spectral error here. And hopefully, as we take the size of our vector space to infinity, these will converge. Or this will converge to that, rather. But then also, if we're trying to project onto this vector space, we need to kind of, figure out how to get from some function. Yeah. So, well, at the moment we're not. Okay, now I'm going to explain what this is. Okay, so we have this projection onto a finite vector space, but to do this right, most projections, if you think about, say, orthogonal projection in L2, say, you think of an integral, right? I'm projecting onto some, say, orthogonal basis. So that's my projection, like Fourier modes or something like this. But to do this, I have to compute this integral. And an integral is, something that requires you to take an infinite amount of points. You've got to take a Riemann sum or something like this. So kind of necessarily we have to, again, because we're on a computer, everything's finite, do some kind of quadrature on this. Quadrature being a very general way. It doesn't have to be a nice kind of quadrature. It can be Monte Carlo, for example. So we also have to think about having a finite number of quadratures, the error associated with that. So we really want this, well, we really want this operator, but we're willing to settle for this because it's a finite dimensional thing that we can represent on a computer, but we can't calculate it. So we have to settle for this operator, KMN, which is basically a quadrature estimate. Okay. So 2 limits. Yes. Yeah, let's say Hausdorff measure, or this will have discrete eigenvalues in the important area of the spectrum So there you can think about convergence of specific eigenvalues. Multiplicity counting kind of way. So yeah, okay. So this is the kind of the challenge. And I would say in general, okay, so we can. This is kind of what I want. The way I want to think about it. I have a particular eigenvalue of this operator, and I want to see how it converges to a particular eigenvalue of that operator. There are obviously two sources of error. So I guess we want to have to consider them a bit separately because they are separate problems, let's say. And we may be very interested in, okay, so firstly, we want to think about we want to study these. This is what I'm going to talk about. Mostly I'll be talking about the sampling error because it's somehow a lot more general. You're just thinking about two matrices converging to each other rather than studying an operator, well, a matrix converging to some infinite dimensional operator whose spectral properties can be very, very different depending on the dynamics. So there's probably no one answer. I don't think there's one answer for this, but there may be sort of one answer for some set of reasonable maps. But anyway, so my question is really, firstly, to what extent can we kind of get a unified, well, let's say a unified error for both of these. So I can say that this error is less than some function of m and n, at least for a representative class. So that's going to be the first half of the talk, the stuff that I then started thinking about this for. So then I'll tell you a little bit about a measure here. And I probably will not get to this very much, but I will be talking about it on the Koopman operator theory seminar on Wednesday, the online thing. So if you're interested, well, either talk to me or come to that. But okay, but first we should probably explain just quickly go over what EDMD is. So let's maybe, there we go. Let's imagine we've got some time. We've been running our map F for a long time. We have some time series from it. This is a very natural thing to do in applications. Maybe you just have some observations, or you have some, something from your giant weather model that you've run. And we assume that it is statistically at equilibrium. So our initial point is sampled from the invariant measure. And then by kind of the measure preserving nature of mu, the rest of them are also all sampled from that measure. Okay, these are not independent, but many kind of, I guess, statistical theory that you get, if you imagine this is independent, do kind of hold up to some modifications if your dynamics is nice. So for example, if it has some kind of, say, some chaotic behavior, usually say hyperbolic chaos, but we believe that it happens for other things as well. So one example of the nice statistical properties you may have here is that this function f has a central limit theorem. So this set of observations has a central limit theorem. So if I take a Birkhoff mean against my time series of some sufficiently nice function, the kind of deviation from its limiting behavior under the Birkhoff-ergodic theorem is a normal distribution. And so if you were at Gary's mini course, like we heard last week, and Gary's mini course, then you would have seen this, kind of a proof of this. We're going to assume this. We're actually going to assume perhaps a little bit more, which is that the kind of hidden machinery that does this, maybe not the, so for example, there's a martingale coboundary decomposition, if any of you have seen this. It's actually a bit different to what Gary did, but okay. We're going to assume that we can do a martingale coboundary decomposition of any of these psi's. Yeah, that's our assumption, which will allow us to get central limit theorems in sort of more detail. Okay, so that's what we know about our map. We need to have a set of functions to project onto. So we're going to choose a bunch of functions, psi1, psi2, up to psi n. These could be whatever, like polynomials, functions, delay functions maybe. And they form the basis of this vector space Vn that we want to project onto. Of course, we can represent any function in this vector space as just like a sum of my basis functions. So I can vectorize it in this form. And this allows us, so there shouldn't be a star there, it's just psi x, it's a row vector times h. And this is how we can kind of compare matrices and operators. So if I ever look at the norm difference between a matrix and an operator, I'm thinking about the matrix represented in function space. All right. So yeah, our hope is really that we can approximate our Koopman operator in this vector space. So Koopman operator is just composition by a function. So I take a function Vn, I compose it with a function f. I sort of want to assume that this function also lies in Vn. This is not true in general. For chaotic systems, in fact, you can always, I mean, it's not even close to being true. You can find functions phi that are like in at least in L2 norm, where k phi is order 1 distance away from this vector in general for reasonable sets Vn. However, we can still try and like project it. So we can, instead of studying the Koopman operator acting on Vn because it's not closed or even particularly close to closed, we can project onto Vn. And so this is kind of, I guess, the source of our dictionary error. And even though this projection might actually meaningfully change these functions, like say in L2, we often find that the spectrum converges because the functions that are being chopped off are kind of uninteresting in some sense. So how do we do this mathematically, kind of concretely? Well, we basically do some least squares approximation. You may remember from first year you have a design matrix and you try and solve it. So we basically construct what we call like, let's start with a covariance matrix. So I look at the covariance between, on my data, between psi j and the Koopman, well, one of my basis functions and any other of my basis functions with the Koopman operator applied to it, which is very nice from data. And I construct a, so I'll look at that, but I'm going to need to kind of, I guess, quotient out by the covariances between the basis functions. We're going to call, so we have a Gram matrix and a cross correlation matrix is what they're often called. So I can vectorize it again because I can think of psi as being like a row vector of all of my dictionary functions. And the least squares projection of my Koopman operator onto this function space using my quadrature nodes. Which is pretty, I mean, it's non-linear, I guess. You've got to invert, but it's a pretty simple formula, and this is something we can actually do quite a lot with. So of course we can, when we're thinking about the data error, we can take the limit as m goes to infinity of these two matrices, well, we can see that they converge to their Birkhoff averages. So just some other matrix like this, and this gives us what our kind of m going to infinity Koopman operator is. And so this is indeed the L2 mu projection of my true Koopman operator onto the subspace, onto this Vn subspace. So the nice thing about this is that these are all just n by n matrices, and if you choose your basis correctly, this is going to be invertible. So, if all of my matrix entries, if I go back, for my matrix again, if all my matrix entries here, these are all just, sums of psi j star times psi k over, over my orbit, right? So this should have a central limit theorem. So the error in this between this and the true value, so that the coefficient entries between of these should just be of order 1 on root m, sorry, central limit theorem. And therefore, kind of the norm of this, or the difference between these two things, in coefficients and therefore in norm, because they're finite dimensional, should also be order 1 on root m. However, it may depend, the constant in front of this may depend on n, where it's nasty, and may actually kind of mess us up meaningfully. Of course, how can we study spectral convergence? Well, I mean, if these converge in norm, then these should also converge. Spectral elements should converge as well. So if this has all simple eigenvalues, which is what I'm assuming for this talk, then our eigenvalues should also converge like this. Maybe with nasty constants.
So I'm a bit confused because your Birkhoff theorem is about the dynamics. Here you just increase the number of points. So how do you choose this point?
How do you choose this point? Well, you assume that your first point is you assume that this is like randomly sampled, like say from the invariant measure. Yeah. So I mean, usually, in applications we want to do this, and we randomly initialize our first point.
So in some sense, you have to know the invariant measure to play this game.
Yeah, I mean, you don't have to. You can start with Lebesgue measure, and then you can run it for a long time, and then yeah, spin it up. Yeah. Okay, so the kind of simple thing to do is, yeah, just say, well, okay, you know, I guess we know that this is order 1 on root m. Maybe we want to know something about this constant. So what I'm going to do is I'm going to define basically the errors between these two, this cross-correlation matrix and its true value, and the Gram matrix and its true value. Data goes to infinity. We know the coefficients are order 1 on root m small in like a kind of, if all our observation functions are bounded and like reasonably nice, these should be like basically uniformly small, the coefficients. But our problem is, right, that we have, if I get back, we have to invert this against that. And then, you know, look at the eigenvalues of this. So we want to kind of boil it down, things down a little bit. So we can show that if I have a lambda, which is an eigenvalue of this finite data, finite observation matrix, I can, you know, do a bunch of manipulations on it. I hope you believe all of these steps. So I can, you know, write Kmn as the Gram inverse times this and multiply that to the right-hand side. I can separate the kind of limiting values of these things from the finite data error values of them. And I can take this on the left-hand side, and I can see that the tilde matrices, right. The tilde matrices are the differences between the infinite data and the finite data one. Yeah. So these should be, you know, somehow, if I took an expectation with respect to my initialization of my time series, the expectation of these guys is 0, and their coefficients are all 1. Okay, so we can rule out, so basically lambda is an eigenvalue of this guy if 1 is an eigenvalue of this matrix here. Okay, so, well, how is that helpful to us? Well, it means that if we know that, say, that the norm of this guy is less than 1, then we know that lambda cannot be an eigenvalue. Well, that this can't have eigenvalue -1 because by the Gelfand theorem. So lambda cannot be an eigenvalue of this. It's kind of a quick and dirty, but mostly pretty effective way, actually, of checking to see if you have an eigenvalue here. Of course, you know, notice that we can conjugate by any matrix. How do you evaluate them? So at the moment, we're just in theory world. Check, theoretically check, but you can somehow like turn this backwards and check. Yeah, there's a method to reverse the polarity. Yes. So in this, well, I mean, up to now, that would apply, yeah. We're going to use some extra theory about these particular maps. Sorry, I'm going to go back. Have I actually talked about this? We're going to use some extra assumptions to get some extra information, so that then maybe you don't need to. Yes. Yeah. Yes. Okay. Get. Yeah, indeed. Okay, so I guess, yes. So this is all very general. And so we do need to introduce something to sort of, you know, say something beyond the solvability complexity index. So let's just start. Let's start with some simple maps, which are uniformly expanding maps of the circle. And if you've never seen these, I will just draw them, explain what they do. So here is, let's say, the interval 0 to 2 pi, and you can imagine it's periodic. Okay, I'm going to look at a function, some functions that map, that are uniformly expanding, which is to say that their derivative is always in norm greater than 1. they're also always, let's say, they're also analytic, and they wrap around. Okay, so here is an example of such a map. They are kind of, let's say, the simplest kind of, certainly the structurally simplest example of a chaotic system. They have a lot of nice properties. If we know anything about a chaotic system, we know it about these ones. They have physical measures mu, which have analytic density. They have a set of Worrell-Polycott resonances that are typically infinite, countably infinite, and accumulate at 0, something like this. They only have one eigen Worrell-Polycott resonance on the unit circle. That's not relevant to us, really. Yeah, here we go. They're nice. So we're going to choose, so there we've chosen a nice map. We're also going to choose some nice observations. So we could say trigonometric polynomials, or equivalently complex exponentials, you know, of order up to n. So this is really pinning it down. This is like the kind of, let's say, one of the simplest working examples. And so I showed in 2025, proved, I guess, that there is, well, okay, there is some Hilbert space, which is like a, let's say, a dual of analytic functions. So quite nasty things like hyperdistributions. But nevertheless, we can define the Koopman operator on this space, and we can show that the norm of finite dimensional approximation converging to K goes down exponentially. And on this space, the spectrum is the Worrell-Polycott resonances plus 0, I guess. And so in particular, there, like, we can show that there are eigenvalues of a Koopman matrix for large enough n that converge exponentially quickly to the Worrell-Polycott resonance. And that's, you know, like, for each of these, there is one of these, and for each of these, there's one of these.
So in this space,
Space
K is
H, is it different from the space that we use this, Oscar?
Did you use the Hilbert space?
Yeah.
Hilbert Hardy space. Yeah, it's the same space. Yeah.
So what's the different result to what we?
So the difference is that this, so for you guys, you were looking at Lebesgue, like your mu was Lebesgue measure. It had to be Lebesgue. Whereas this is actually for mu, it can be any analytic, it can be any measure with a density. So in particular, it can be the physical measure. Okay. So it doesn't look like much from the outside, but there was some work required to like get that you had to go into orthogonal polynomial theory to make it work. But yes, so I mean, like Julia and Oscar had this, Oscar Bantlow had this, maybe Wolfram used, okay, yeah, had this result, but assuming that your mu was Lebesgue measure. Yeah. Yes, it's compact, yeah. So, you know, it's, yeah, I guess you think about the dual, it's like it's the Perrin-Frobenius operator, transfer operator, whatever, acting on a space of, like a Hardy space. Yes. So if you've been around the transfer operator traps, this is really nothing new. It's just the dual of something that everyone kind of knows. I mean, the fact that this is compact anyway, and that you can approximate it, but this particular approximation. Okay. So, all right. So we can go. Okay. So in particular, we know that the eigenvalues therefore have to converge exponentially quickly. So how do we deal with the data error? So that's the dictionary error. We want the data error. Let's go back to this. So recall that we can kind of rule out lambda being in our spectrum if this is, we can find some q so that this is true. Let's just set q to be 1. Obviously, this is upper bounded then by this product. And so we just have to understand what all these terms do. Now, why do I care about ruling it out? So if I have, let's say, some eigenvalues of my of my matrix, and I can say, well, I know that in some areas far away from these eigenvalues, a specific distance, that I don't have any spectrum of my sigma m, then I know that my eigenvalues have to live close by. And of course, you're interested in, you know, like whether I can actually, what's the word, spectral visibility or something. You know, you have to check that you actually, you know, your perturbation. You have to check whether your perturbation also has an eigenvalue in there, but I mean, maybe a bit of extra work will get that for you from what I have here. Okay. So basically we can kind of, by ruling out large areas of spectrum, we can then get some kind of spectral, where large areas of the complex plane where lambda cannot be an eigenvalue of this, we can somehow like rule in where the eigenvalues have to go. Okay, so we've got to bound all these things. I mean, this is just like some, I don't know, whatever, functional analysis chase, I don't know, you know, norm chasing stuff. This here is well, Gn is a turbulence matrix containing the Fourier coefficients of my invariant measure, which we know is analytic. So this is a very nice matrix, and its norm is uniformly bounded as n goes to infinity. Okay, so we don't have to really worry about this. This gram matrix is a super nice gram matrix. We have a very stable basis. From a more applied perspective, that's what you'd say. Okay, so then we have to consider the resolvent of our Koopman operator. So we got these out of that, of Gn, Kn. And then we have to think about basically the norm error of Gmn minus, or the error in Gmn minus the error in Amn. So we know that the coefficients of these guys are order square root n, m, order 1 on root m, sorry, and we know that lambda isn't very big. So this is a matrix here whose coefficients are small in a way we can control very nicely. Okay, that's kind of the picture. So we kind of firstly want to know what this is. That perhaps maybe to many people. Yes?
Do you have to assume that the true system is discrete spectral or continuous spectral?
The true, exactly. So that's what I'm going to get to now. So I mean, because these are all matrices, right? These guys all have discrete spectrum, but the kind of the feeling is that Kn here is close to the true Koopman operator K in certain norms. So yeah, you have to worry about discrete versus continuous spectrum there. So again, if we're looking at this kind of L2 mu projection, we can show that Kn is close to K, not just in that dual of analytic function spaces, but also in this space here, maybe a little more familiar. So we look at functions and we take the norm, we downweight. Oh gosh, sorry, that should be phi hat of n. So we look at the Fourier coefficients of a function, we downweight by 1 plus n squared. So if we're looking at these sine and cosine bases, that's like, yeah, we downweight by like basically n to the minus s, the nth coefficient by n to the minus s. And it turns out that our Koopman operator is quasi-compact in that space. And in particular, you can more or less approximate Kn. You can find Kn, an operator that kind of contains Kn that's close to K in this norm. So hopefully, therefore, our resolvent here is kind of sensible. To do this, if we want to kind of, in this norm, in H minus S, but here we have L2, so we have to kind of pay a penalty, really. So because this is, only contains, sine and cosine functions up to order n, we can actually compare these norms on our space, on a dictionary space with this penalty. That should be just to the S on 2. There shouldn't be a minus there. Can I draw on this? Yeah, it's probably not a point. Sorry? Yes, that's plus S on 2, yeah. Yes. Okay. So what can we do with this? Okay, so that's kind of cool, right? So that means that we can compare if we know that lambda I minus Kn inverse is, let's say, reasonable in H minus S, we can just like transfer it to this with an n to the S penalty. However, K is in these subglyph spaces, the Koopman operator is only quasi-compact, which means that if I look at its spectrum, here is my, my beautiful spectrum, which contains all of my real Polycott resonances, and this is what I get in this sort of, space of analytic, well, dual to analytic functions. But if I look at H minus S, I actually have some essential spectrum. And this essential spectrum, you know, you can bound it inside a certain essential spectral radius. Essential spectral radius, which we know is, I believe, equal to R, we're going to call it R of S. So this radius here depends on S. It's actually, we can write it down in terms of some pressure functions, but it's a decreasing function of S. It looks very approximately like, this is not a, you know, a Taylor series or anything. It looks something like e to the minus the Lyapunov exponent of this of the system times S. That's broadly what it is. So as you increase S, you shrink your essential spectral radius. Okay, but this is still 1D expanding. Yeah, but I mean, like you can imagine, you can expect this to some extent to generalize to other systems. Yes. Yes. Yeah. Yes. So I mean, okay, right. So in practice, you would never try and find the resonances these way. You'd use like whatever, like Chebyshev-Lagrange or something. But yeah, exactly. Yeah. But this is just like I would like to study a simple system to see like what Koopman does and like okay, so I guess for this, so this is true. This is true of the of my true Koopman operator, right? But I projected it onto the finite dimensional subspace, and maybe I've extended it so I can make sense of quasi-compactness. So in that case, nevertheless, we kind of, because K and Kn are kind of close, you can imagine this to be Kn, you know, we still get the same kind of bounds on our resolvent. I guess, you know, if we're away from this essential spectrum, the norm of my resolvent of lambda I minus K inverse should, you know, be something like 1 on the distance. Like there should be like 1 on the distance to the nearest spectrum times some penalty you pay because you're not normal. And this is still kind of true if you're simply just close to the operator in norm. So what we can say, more or less, is that the norm of this guy, this thing that we need to bound for to kind of isolate bits of spectrum for our data-driven operator, is bounded by the penalties we pay to convert between L2 and HS. And then this here is bounded by something like the distance spectrum. Okay. For any S, so that wherever we are for if we choose a particular lambda, for any S, so that our essential spectrum doesn't kind of wash us out, so that we're away from the essential spectrum. Okay. So, and of course, you know, you notice here as I make lambda smaller, I have to make S bigger because R is this radius is decreasing. To make S bigger, so my penalty in N gets worse and worse and worse. All right. Okay, where were we? So I know this is bounded. This is like N to the S times the distance to the spectrum. I need to know what this is. And here was the bit that actually was very nice to generalize. So I can think of this here as, so each of these is like a matrix that's like a Birkhoff average of some other matrices. I should just go back to this. Yeah, see, this is a matrix function of xm, so is this. These are both Birkhoff sums of them. If I take a kind of difference of them, then so lambda times gmn minus a times amn without the tildes is this guy. But then I subtract off their kind of limiting behaviors and I get this. Okay. Okay, right. And if I think about this in a kind of probabilistic sense, I've got the difference between something and its expectation. I want to do some kind of probability theory on this. You know, if these were scalars, I just have a central limit theorem, right? But if I'm interested in the norm of this guy, I need to, well, maybe I want to know some kind of extra super cool central limit theorem. And maybe you could go to random matrix theory where you're like, the entries of these are like order 1 on root m. What's the norm of like a n by n matrix containing a bunch of like normal random variables? It scales as the square root of n. And this, I'm not going to, perhaps I don't have time to go too much into this, but this is actually a reasonable assumption to make. So certainly if you have independent matrix functions, you can bound, let's say, the kind of expected size of the norm of like some mean zero variables as basically like 1 on root m times, it should be times, we're not dividing by sigma squared, times this parameter here, which is looking at kind of the expected value of the kind of covariances between these two matrices, broadly speaking. So most of these parameters in practice you can't really ignore, but you can to first order ignore. But this is kind of the parameter that tells you the expected size of the norm of your matrix divided by root n. So they would correspond to so in our case, we're sampling from data, so we're not what's the word? We're not these aren't independent, but you can turn them into martingales, and then you can get this result. Although at least for chaotic systems, you have to think about a difference process. So you actually you don't quite get this. I haven't been able to prove this tightly, but you can prove this with losing a little bit. Yeah. Yeah. Yes. So, but these are for matrices. The only thing is that, yeah, like I guess there's no actually, yeah, this is a gap. So when I was doing this, I assumed that like you could do the set like the martingale. You know, the theory that they use is like you have a martingale, you bound it using you actually put in the martingale difference function here, but actually that I guess that's not how you do. We have done it in chaotic systems, like so maybe then we use cones or something like this. But then that you like, what is a cone of a matrix? So there's a gap there that's interesting. That I thought was interesting. Yeah. Yeah. Okay. So then I guess like again, I could, because of that gap, I couldn't actually show this for like this is not a theorem, but like it's sort of what I'd expect to see. That you actually, instead of having this kind of correlation, well, it's kind of like a correlation, you actually need to take a bunch of cross covariances, like so. And in our case, at least, you can, well, anyway, you can show that in our case, you can show that these are order n, and then you can get this bound here. So allowing yourself to lose a little bit because we don't have a. You can only bound the martingale differences, or the prediction or whatever is the forward estimate of the variance. Okay, so in the end, what we end up with is that this kind of this data-based error. Sorry, I've got my colors mixed up. That should be yellow. This should be this. The data error. This is order root n on m basically. This is order n to the s lambda. We could just fold the root n into that, the log n into that. And so in particular, the, I guess, distance between any lambda that's not in, well, okay, we know that if lambda is bigger than this, then this thing here has to be less than 1, and so lambda's not in the spectrum. So we have a kind of nice bound on where our spectrum cannot be, and therefore where our spectrum must be. With a little bit of extra work. Okay, so in particular, the difference between the data-driven error and the infinite data but finite dictionary error is this. And so if we put it all together, we get this behavior, this kind of error. So in this case, this very nice case, our dictionary error is tiny. It is really dominated by the data error. And the data error is something that we really can't make better because essentially you're, I guess, trying to study eigenvalues, say lambda k that is small. You really have to study your Koopman operator in a high dimensional space, in a high regularity space, so lots of derivatives, and studying and doing that, like kind of database approximation to get high derivatives correctly is hard. It requires a lot of data. So numerically, we actually see this. So you can see here that to see different lambdas, we need to take different scalings between n and m, depending on what the absolute value of lambda is. And so if I do this, so I'm increasing m here, like I'm making it 10 times bigger every time, but n here I might be taking, here I'm making it 5 times bigger, here I'm making it 3 times bigger, here I'm making it twice as big. So these are different, power scalings. And you can see that the spectrum you kind of converge to, if you take, I guess, okay, so I've taken like a lot of different time series, and for each of those constructed different Koopman operators, and I've just taken the union of all the spectra. You can see that you converge to basically blobs of spectra, but for, let's say, more parsimonious scalings of n, so I'm like fitting it to fitting my data to less basis functions, I see more of my spectrum than I would.
Yeah.
Where's my central spectral radius found? In the pictures. Look, it's in practice. This is. I don't think this is. It's sort of. Kind of. It's outside this block. It's not.
The blob is inside the central spectrum. Yeah, I think so.
Don't understand. The blob is so I'm looking inside the central spectral radius, but for which space? For the HS.
So HS. So I guess you can imagine S changes. I'm taking, yeah. S is different for each of these. Maybe I could have actually written what S could have been up here. Yeah.
But I thought you were using Calderon before to the approximation for lambdas.
Yeah.
So that was a theorem. That was a theorem bounding my error, but that's not necessarily. That theorem is not necessarily tight. This is just like a. Like this is true, right? But I know this is true, but like I don't. It could actually. Things could be better. But I think like things are not going to be like qualitatively different to this. Like you will get some. You should get some.
Although that's not written.
Okay, but like it's meaningful. All these blobs are meaningful, even though they're inside the essential spectrum.
Yeah. Well, I mean, I guess they're telling you. I think they're telling you something about the central spectrum.
The other question I had was I missed what happened to the log in your formula. The log.
It got incorporated into the power.
I think you flicked through something very quickly.
But I'm confused because I was thinking that the essential spectrum is just. I was thinking that the essential spectrum is just a disk. It's not always a disk. Apparently not on your picture.
Yeah, I don't know. I mean, so I guess one answer to that is maybe it's not actually showing the essentials, just looking at the essential spectrum. It's looking at something different that lives as like that is inside it.
Can I ask a question?
Yeah.
I mean, you're just maybe approximating the essential spectrum. That's one possibility. Otherwise, if not, how do you know this is not spectral pollution? You are inside the context of the essential spectrum.
You don't. I mean,
it's spectral pollution.
yes.
How can you exclude that?
That's a very good question. I mean, so I guess typically like in I guess the chaos. I mean, correct me if I'm wrong, but it's like most of the time we just like look at. In transfer operator world, we just like look at the discrete spectrum, and then we say there is a radius inside which the essential spectrum lives, and we don't know what's going on in there. Sometimes there's results saying that the essential spectrum fills it, but at least in terms of approximation, the approximation theory of transfer operators, I don't think anyone's like proved that.
Yeah, any convergence results there.
Because I mean, if you do finite dimensional approximations of things that are infinite dimensional, it's natural that you approximate the essential spectrum if you do it right.
Yes.
But what does it mean for your problem?
What does it mean for the problem?
So I guess in the problem it just means that you if there are like true resonances in like you know, which you get by changing your function space, and which are kind of stable under your function space. So it's just like you know, your essential spectrum grows and recedes, a bit like PDEs or whatever. You don't see them in these, you know, for these scalings, right? Like here we could see, I mean, here we could see these two dots to the right. Here we can't, and that's, yeah.
Because we haven't taken the right scale.
So in this particular problem, there are no Wormell polygon resonances, or what's the?
There are, so there are at least 4. I mean, there's an infinite number of them. Maybe if in a different figure, which I didn't put on this slide, you can actually, I've calculated them. So they all kind of, they form like a kind of weird claw.
Also, the essential spectral radius is sort of like surrounding only the blob in the very middle, right?
Yeah, exactly. Yeah. So they kind of look a bit like this problem there. 0. They look like this, but the blob has covered. The blob has mostly covered them, and so here you can see that there's
So I don't know, because there is this old paper, I don't know, maybe Collet, Diesel or someone like that they show, well, for C1, for C2 map, and then they look at the essential spectrum in C1, and they show that it's really a disk. But maybe it doesn't work for higher regularity. I never really saw it.
I don't know.
I mean, I don't understand this shape. What they are kind of funny, right? I don't understand what they are.
Yeah. So I mean, I guess one answer is maybe the essential spectrum is a disk, but this numerical method is not actually
In
seeing
the essential spectrum. That's another possibility.
Then what? Yes, possible. But what you see?
Yeah.
Let's see.
Julia?
So you're taking some map for which you know the spectrum explicitly?
Not explicitly, but I could calculate it using Chebyshev.
So it could be that the eigenvalue, so I mean, it could be that in some spectral pollution, if it's like outside of the display, if you look at this orange picture in the,
Pretty small.
yeah, the ones, so you get the first one or something like that.
Yeah, first of all.
I mean, it could also be that like you need to take, if you take M and N higher, then you will end up with a disk, and this is just taking a while to converge. Really high S. Well, the problem is that like to do that, either your N is really small, so you're not actually like you have a this is big, so you have a substantial dictionary error, or N is
Stupidly large and it's not.
So because N is the size of the matrix, right? Do I correct? So so in some sense over there you have many more values. I mean, in this picture, but also the S is changing. No, I don't remember anymore. I'm sorry.
Yeah.
The S is different from different color, right?
Yeah, so I guess here I'm thinking about N is like N to the whatever the rest of one. And I'm changing this.
You change that.
So S is smaller here.
But it's difficult to compare, right? Because since the number of value changes from column to column, also then. Because I see. Sorry, I see. N is N.
Here, we're using the maps that have like
Yeah, but it could be.
generally, but the pictures
You
are
keep fixed
symmetric
N, change
about the real axis.
fix.
Why is that? Why do you see it look like two guys that have the same race?
so they're like real eigenvalues. So complex conjugate eigenvalues. So the reason you get complex conjugate eigenvalues is that these are real maps.
Oh, okay. So you're gonna have spiral case.
Different colors, but maybe different.
Sorry, one last question. Do you have by any chance a picture in which you keep fix N and you change M?
Yes, I do.
Because then you could at least see the more or less same number of eigenvalues, and then maybe it's easy to understand the difference.
Yeah. So where's the picture? So this just shows the leading eigenvalues, but I think that must have been that one. Number.
Okay, so in this case I've called n, like this is actually m, even though it's called n here, and I've just shown the leading eigenvalues, but you can see that as you increase the number of data points while fixing the number of basis functions, you get convergence.
This is the number of points, right?
Okay. So,
I mean, it's an advantage. You have these super smooth, like Fourier, like bases, and then you're trying to approximate things in h minus 1 million or something.
yes, no, I agree. This is not a sensible
Right,
thing to do.
with that smooth basis. With a rougher basis.
With a rougher basis, well, then you couldn't see things in H1 million. You couldn't see things in H1 million.
But
But if you
you're
just want-
approximating in h minus 1 million, actually.
Well, I mean, this basis is also good for approximating in h minus 1 as well, right? But then h minus 1 will have an essential spectral radius out inside which you can't see. And in practice, you only care about stuff in h minus 1. Like the rest, unless you're interested in like.
Use the stuff, I guess it would correspond here to h minus 1 million. Or h minus.
H minus, yeah, omega or something, yeah. Yeah, so okay, I should say.
Because you have a super smooth basis and you're trying to approximate really rough things.
But it's not because you have a super smooth function, it's basis. You can have a super smooth basis and do it in like the space of rough functions and be as good as any other basis in that space.
Depends on things, I guess.
Sure, I mean, I think Fourier bases are like as good as you are going to get in any reasonable, like they're comparably good, right? I mean, computationally they may be, they're not sparse, but the thing is that, like, what's actually happening is you have to work in the Banach space. This is about the Banach space that you were forced to work in, not the basis itself. Yeah. Cool. All right. Well, I guess I don't really have time to talk about the thing, but basically, I just want, like, if you'll just give me 5 minutes to plug it. If you'll give me 5 minutes to plug it. So, we can generalize this kind of data-driven idea. So we're not looking at the kind of the dictionary error, just the data error. We can try and think about this in a, like this, as Christiane said, is like very general. So provided that we have a central limit theorem to understand what's going on here, we can actually try and, let's say for any kind of system, we can try and find some Q, which is like a norm. So here, like in this case, we had H minus S norms, but we could have some other norm we don't understand. We can just say, well, we just need to find any norm for which this error, this kind of, the norm of this guy is less than 1. And thereby rule out spectrum. Okay, yes, okay. And the way that we can do this is, well, okay, I mean, we want to find some Q so that this is small. In general, we can't know this necessarily because we need to know this kind of deviation, well, both the data limit and the infinite data limit and the finite data matrices, but we can sort of quantify the kind of statistical behavior of this using our using that kind of matrix central limit theorem results. And if we look at this function here, this kind of set of basically expectations, these kind of variance parameters of our matrices, we can bound basically the chance that we get an eigenvalue lambda, or an eigenvalue close to lambda, by the probability that this norm is bigger than 1, using this parameter here. Of course, this is for a specific Q. We may want to optimize over Q so that, to minimize this probability, so get the tightest kind of tail bounds we can get. And to do that, we basically get this operator, well, this quantity P of lambda, by magic of, how would I say, by the magic of positive, cone-preserving matrices, because these Qs, we can assume that these Qs, say, induce a norm, are positive definite. We can actually find this P of lambda here as the spectral radius of an operator S lambda Q, where we can build these functions here, W lambda, from either from our data or from like our true a true knowledge of like, you know, the Koopman operator and quadratures of systems. And in particular, you can get a kind of, yeah, sort of spectral exclusion result where you're interested in, do I see any eigenvalues of my data-driven, sorry, I changed the notation because I copied this from another talk, of my data-driven Koopman operator, my finite data. I can exclude spectrum from an area E based on the value of this quantity along the boundary of E. So this is actually like a pseudo-spectrum. So here is my quantity P, and you can see that where P is small, well, okay, where P is small, I tend to have C eigenvalues. So red is finite data. So red is infinite data. White is different versions of the finite data. So this is just like a plot, like we saw last time in the that we were talking about with the 1D expanding maps. But this is for something. This is also a 1D expanding map, but I'll show you a Lorentz example quickly. And you can see that indeed, like this is obviously a pretty complicated pattern here, like where these eigenvalues go, but it is well approximated by this P quantity, and it's well approximated for different numbers of basis functions and data points. And in fact, what you can also see is that if you want to count, like, well, okay, sorry, you can, if you want to count eigenvalues of the data-driven operator versus the true operator, there is a counting thing. So if I have an area here where this P of lambda thing, which is like, again, it's like a pseudo-spectrum, where it's small, I can see that the number, like I have this sort of well here where I have my value, my pseudo-spectral indicator, P, is small, and I can see that there are two, say, data-driven eigenvalues, and I can see that with very high probability, there are also two true eigenvalues, vice versa. So it goes both ways. This is actually not this true P operator, which requires me to take various expectations. I just took sample expectations. So I have an estimator of this quantity, and I can see that, yeah, I can firstly bound where, like, I guess, where my spectrum is likely to be.
How are the different data-driven approximation?
So this is all done using like some kind of EDMD.
So do you change the basis function, and that's how you get a different K?
I get a different K. Yeah.
Because you say you have like 100K at.
Yeah, so I have not 100.
So I took a different number of basis elements here, yeah.
But
So I changed my dictionary size.
so 100 versions of K hat. I assume each K hat is from an EDMD.
Yeah.
So do you change the basis?
Oh no, I just changed my sampling. I changed my initialization, so I get a different time series and not. So like, yeah.
How well do these gray blobs compare to what we could obtain, for instance, with epsilon pseudospectrum of your approximated matrix?
The epsilon pseudospectrum is generally much larger, and the reason for this, I guess, is that your well, okay, so your norm blows. You don't know what epsilon to choose to start with, and you don't know what norm to choose to start with necessarily, because maybe your basis, yeah. Yeah, so this kind of basically finds the norm for, like, the best norm for you based on the variation of your data. It's kind of like, yeah, adaptive in that sense. Yeah, so we have a bunch of theorems saying that you can, yeah, you get some nice statistical behavior. You can even really do a statistical test for using this estimator for where your true eigenvalues are. So you actually know, here I plotted the value of P hat for different true eigenvalues, like my estimator of P hat for different true eigenvalues, and I can see that I get some kind of chi-squared like tail behavior. They're all of order 1, and they're very rarely much bigger than 2. So actually, this is not a pseudospectrum thing where you're like, this is small, therefore it must be there. This is actually like, this is bigger than 2, therefore there is a, you know, small, or this is bigger than 4, therefore there's like an e to the minus 4 probability that it's outside. You can do this with Lorentz. I've done it with a fluid flow to look at where the true eigenvalues are. And you can actually also see, like, and this isn't proven, and it would be very interesting, like, if anyone's interested in working on this, that would be really cool. You can actually also see that eigenvalues that are kind of separated by this p hat of lambda. So I think I've changed the color. Oh no, yes, I've changed the thing of color now. So eigenvalues in islands of small p hat lambda tend to have nicely resolved eigenfunctions, whereas eigenvalues that are sort of, you know, in like one large blob of small p hat lambda, which is kind of, you know, where we might expect to see some sort of essential spectrum, or, you know, everything's mixed together, tend to kind of look a bit less nice. So what's it of this? So these are this is a plot of the eigenfunctions I got just by, like, you know, from finite data. It's the complex modulus, yeah, and the color is there's a complex angle, and the color is the modulus. And you see kind of weird striations for these ones that are kind of in the middle, like 8 or 10 even. I haven't plotted 10 there, but yeah, which suggests that maybe that's kind of data sampling error. And this is all in a package, so you can take your favorite data set and you can compute these kinds of pseudospectra, and it's really quite efficient. Yeah.
Okay.
Have you tried to reconstruct correlation functions to check whether these eigenvalues are physically meaningful? Let's say for the Lorentz 63 system.
Yeah, whether these eigen. So I've compared them to what I get if I take really large n. If I just take a lot of data and a lot of basis functions, and these ones 1, 2, 3, 4 are all correct. I think maybe sort of a couple of the ones in here might also be correct. So I will say, like, it's not perfect. It probably underestimates the error probabilities by a factor of 2. So there are probably a couple of ones in here that do make sense, but then a lot of them also. So I guess that's statistics, right? Sometimes you can't see everything, but it does a pretty good job on seeing the ones that should be there.
So let's thank Caroline again.